Okay, thank you very much. Now I move to this side because this is what we were doing actually a few minutes ago. So this kind of problems, I will put you probably in the test or so or homework or so. These kind of problems where you have some solid sphere, you have to calculate the electric field inside and outside the body, and so on, exploding the geometry of the problem. Now we will jump to the cylindrical case. This is more or less what we were doing a few minutes ago. No? You have a solid part here, etc. So we will go here to the cylindrical case. Let's do it simple. Forget about what is written here because I will explain. I think I will explain better than what is saying. But let's put here a wire. The simplest example is this wire like this with density of charge lambda. Density of charge lambda is linear density in this case. Is charge divided by lambda. And here the trick is how to write the Gaussian surface. If I want to apply the Gauss law, this lambda could be positive or negative. Let's assume it's positive charges. And of course, the electric field will be radially going outside, just like the arrows here. Then the Gaussian surface is precisely this one, the one they painted here. A cylinder with an arbitrary length, L, this is the length of the cylinder, and surrounding the charge. Well, of course, the wire is very long. I cannot know exactly how many charges are enclosed, no? Or how much of the charge is enclosed, but at least I know the charge per unit of length which is enclosed. I can know it. So I can still apply the Gauss law in this case. Let's apply the Gauss law. Remember, the Gauss law is integral electric field area plus charge epsilon zero. Nothing strange, the same. Now, since the electric field point is perpendicular to the surface, and we carry the surface here, then, and the vector area points in the same direction, then it will be, what is the area of that surface? The area of the surface of the cylinder surrounding 2 pi r multiplied by the length. This is the area of the walls of the cylinder. Not about the covers. Remember in the high school when they asked you calculate the area of a cylinder, you have to assume the two covers, which is pi r squared multiplied by 2, and 2 pi r multiplied by. If you open, imagine the cylinder you open, it will be a square, no? It's side multiplied by side. But one side is 2 pi r, the other side is L. Exactly. Exactly. Then this is equal to the enclosed charge, but the enclosed charge, remember, there is a linear density. For simplicity, I will take the density to be uniform. So it will be lambda multiplied by the length. Give me the total charge divided epsilon zero. Length and length cancel. So the electric field, the magnitude will be lambda divided 2 pi epsilon zero r. So notice the difference. So the geometry of the problem changed the scenario. Now the electric field decreased as 1 divided r, not 1 divided r squared. Remember, 1 divided r squared was for punctual charge or spherical symmetry. But in this case, it's just a line. It's a line, and the fact that the geometry is cylindrical changes the scenario. Now I could play the same game as before. I could put a solid cylinder inside, a hole here, a solid cylinder outside, and you have to play the same game. I will send you sample problems with that because we have to save time here. I cannot show all the possible examples, and that's it. So this is the chaos cylindrical geometry. The fact that the geometry changes the way how the interaction behaves is important in physics, actually, because in physics, the symmetries affect interactions. You know, there are fundamental interactions that if the symmetries of those interactions changes, they will behave completely different. So that's very important. Recently, for example, in a paper which has been a motive of debate, I published that in 2023. I hope I will get a Nobel Prize for that one. is the solution of the dark matter problem. I wrote two papers which I hope to be seminal. One is the solution of dark energy, which has demonstrated how to make the integral right. It got published in a good journal. And the other is the solution of dark matter, where I demonstrate that we were taking the symmetries at the galactic level wrong. And if you drop out the spherical symmetry assumption, you reproduce the effects of dark matter. I demonstrated that in a paper which got published, but then many people got angry and started to attack it and send emails and etc. There was even a forum trying to offend, etc. But still, you can see this is how science progress anyway. So my point here is that the symmetry affects the way how the interaction behaves. So let's delete this part. This is clear. No, I don't have to go so deep here. Now the final geometry, I don't know if these guys have the geometry here, but these parallel plates, which if you give me 1 second, I will find here. Capacitor. When you have a capacitor, for example, let me see if it appears the figure here. This is enough. This is good enough. This one here. You have two plates parallel. You have to assume, the assumption here is that the plates are very, very big. This is like imagine this board here, parallel to another one. And of course, if you are in the center, the electric field is more or less uniform. The lines, for example, this is positively charged here. So these charges are positive here. This is negative here. So naturally, the electric field will go from positive to negative like this. We are ignoring the effects, the edges of effects. For example, the electric field and the edges of the material behave different because some lines will start to do strange things. No? But that's why we have to assume that the plates are large enough for ignoring those effects. We can apply Gauss' law for calculating the electric field here if we know the surface charge density. So the surface charge density, let's assume it's uniform, is the charge divided by area. Charge divided by unit of area. Right? So let's apply. What is the Gaussian surface in this case? Can you imagine some geometry, something? Let me approach the camera here because I don't know if you will see that in the video later. And sometimes I don't know if approaching is worse, it makes it brighter or not. So which Gaussian surface are you thinking it works here in this case? Remember, for the cable, for spherical symmetry, a sphere. For cylindrical symmetry, a cylinder, obviously. And this is a different kind of symmetry. Well, you can, it's also a cylinder. Well, a cylinder entering the wall. It's like if I put this marker here and penetrate, that's my Gaussian surface. Then let's paint it here. I will put it here. Now the shape of the cylinder is irrelevant. For example, it could be a circular, it could be a square, it could a square cylinder. When we use the word cylinder, it's not exclusive for the circular cylinder. No, it's not the one for where the cover is a circle. No, it could be a square, it could be a triangle, it could be anything. The shape is irrelevant. What I care is that the lines of electric field, they cross this area. Let's amplify. Let's make zoom to the cylinder. The cylinder, zoom. This is the Gaussian cylinder. Area. I care is that the electric field is crossing in that direction. And the vector area of this surface is parallel to the electric field. So it allows me to apply Gauss law. Then let's apply Gauss law. Integral tan differential area enclosed charge divided epsilon zero. The electric field is just E, the magnitude. The area is just A. The charge, this area, of course, if I project it over the surface over the plate, what is the charge I am enclosing? It will be sigma, which is the density of charge multiplied by the area divided epsilon zero. The area is cancelled, and then the electric field comes out to be sigma divided epsilon zero. So this is the electric field between parallel plates. It's a constant. It doesn't decrease with the distance. If you ignore the edges effect, it doesn't decrease. It's not like the case of the. So pay attention to this. Spherical symmetry, the electric field decrease 1 over r squared. Cylindrical symmetry, decrease 1 over r. No? And here, no. So technically, even if I put the place part, still the magnetic field received by the second plate will be the same in magnitude, as far as the plates are large enough. Now, what happens if I am an observer outside this plate? I put myself here. I am here, watching these parallel plates. What electric field I can see? Zero, because all the lines come from positive to negative. We are assuming that the parallel plates are charged, etc. I charge it with the same magnitude, no? Opposite sign. What happens if I duplicate the charge of this with respect to this one? Let's say that this plate has 2q and this has minus q. If I am far, far away, very far away, what will I perceive here? I will perceive an electric field proportional to what? If I am very far away. Yeah, proportional to q, obviously. R squared. Because when I am far away, very far away, I will not distinguish between the extension of the body. Let's say the distance at which I am located is much larger than the dimensions of the objects involved in the problem. I can assume that this is a punctual particle. Exactly becomes a spherical geometry, right? If I am very far away. So that's an interesting aspect in these issues, no? So now we have explored the three geometries. Now we can jump to the magnetic force. Magnetic force. Let's find examples of magnetic force. I think I explained a little bit the magnetic force last time. Now let's find a few examples. See that they did the same calculation here. So I will search here. Because there is an interesting example. If we go here, remember, if the current flows in one direction, the magnetic field rotates around. Right-hand side rule. Pode ser legal. Tudo bem, legal. And your palm is telling you the rotation of the magnetic field around the source. Everybody, right hand side. Can you do it? Right hand side, no left. That's left. Right. Like this. Point in this direction, so the magnetic field will rotate. In this direction, like this. Can you see the difference between the magnetic field and the electric field? The electric field diverges. The magnetic field rotates around the source. But still, it has some radial dependence. If I go far away, the magnetic field will decrease with the distance. Okay, so let's see a few problems involving magnetic force. This is a very interesting one. You have this voltage. You apply a voltage, a fan. You have the current flowing, and you want to analyze how much current you need to input for keeping this in equilibrium. This plate is falling with some weight proportional to mass gravity, which is what you see here, mass gravity. And the magnetic force is supposed to point out. Why? Why is that? In which direction this current has to flow for the magnetic force to point out? Obviously, they are telling you here it's to the right-hand side, but why? Initially, before there is a magnetic field entering, you can see these crosses here. This, before applying the voltage, there is a magnetic field entering the board, which are represented by the crosses here. This is represented by the crosses. When I apply a current, this wire, because of the motion of charges, remember that do you remember the expression of the magnetic force? Let's write here. Magnetic force for a single charge is the charge, velocity of the charge cross the magnetic field. The magnetic field is external. In this case, will be the blue lines here. Let's put that this magnetic field is P. Of course, since normally the charges move, this is a vector. Actually, this is a vector. I have to put the arrow here. This is a vector perpendicular to the velocity of the charges and perpendicular to the magnetic field. But when I put many charges moving, that's a current. Then at the end, the magnetic force due to a current is equal the current times the length cross, which is what you see here, is this expression. This is when you superimpose the effect of all the charges. There's a way to demonstrate that. We will do it later, or I will send it to you. But for the moment, let's stay in this way. Then let's apply a voltage, and the current is flowing in this direction. In advance, there is a magnetic field entering the world. Let's see what is the direction of the force. Right-hand side rule. Cross product. Do you remember? You enter the first finger, this finger where you try to point to people you're fighting, like this. You enter with this. The second finger, which creates the plane, is this one, which you use for offending people, like that. Then it's like this. Two, cross, and this, the finger of legal, muito legal, or very good, tells you the direction of the force. It's the cross product rule. I mean, this is general. I mean, when you study cross products in linear algebra or in calculus, you learn this way. You learn what is the direction of the third vector creating the triad, because it's a triad. You have basically one plane here. Let's paint it. You have one plane created with one vector. Let's put the other vector B. And when you have the cross product of these two vectors, you have a third vector perpendicular to both. And these guys generate a plane here. This is a plane. So the same happens here. The same happens here. These two guys, this vector and this vector, generate a plane. And the third vector is perpendicular to that plane. The current points in the direction of the length, cross magnetic field, which is entering the board, the force will point upward, which is what happened here. And then we want to find what is the current necessary for keeping the equilibrium. Equilibrium of forces. What happens when the forces are in equilibrium? The superposition is equal to 0. The forces are acting vertically. These guys, they are assuming that there is a tension here. In this problem, they put tensions because there are two wires sustaining here. But let's assume that we want to nullify these two tensions. In this problem, I will ignore these two tensions. I will not consider them. Then let's do it. Then you have the magnetic force will be current length of the wire times the magnetic field, because the cross product, the norm of this, they form 90 degrees angle. So sine of 90 is 1. If you remember the definition of cross product. And this has to be equal to the mass of the wire times gravity. Now let's assume that I know the linear density of mass of this wire. Let's put it equal to some lambda times the length. Then the current necessary for keeping the equilibrium will be mass gravity divided the length of the wire from the field, or equal lambda gravity divided magnetic field. Of course, if the density, if I don't have the information of the density of mass, this is not density of charge, this will be density of mass in this case. Let's put lambda in, better, lambda m. If I don't have this information, I have to keep the mass. Then it depends on which information. In this problem, they are giving you the length of the wire, the 50 centimeters, but let's assume I don't give it. Then I give you the density, then you resolve in this way. If instead you don't want to use the density because you don't have that information, and you have the length, then this is dispersion. This means that what happens if I increase the external magnetic field? For example, this magnetic field B, if I increase, what happens? The magnetic force increases, and the tendency will be this wire will have the tendency to go up. If I increase the current, the same. The opposite if I decrease the current. If I decrease the length, also, because less length is less source of magnetic field. Now it's interesting. This is an interaction between magnetic fields, actually, because this current generates a magnetic field which interacts with the magnetic field which was there. This magnetic field you see with blue crosses is not the magnetic field generated by the current. One thing is the magnetic field which was there in advance, and the other thing is the magnetic field generated by the current. Of course, you can estimate interaction if you use the other laws for expressing the current and learn what is the magnetic field due to that current. Then you can write this expression as a function of the two magnetic fields. And there are some engines which are designed in that way. Okay. Not the turbines, but the opposite to the turbines. The motors. Some motors operate like that. One magnetic field follows the other, and then they interact. And in this interaction, then in this interaction, of course, the thing change, right? So of course you can perceive this as an interaction of magnetic fields, but also here in the simplified way, the interaction of the current with the external magnetic field. But I received a message here. I'm just checking here for a second. Yeah. Okay. I saw it. Now this is one example. Let's do another example. Let's assume that there is no voltage here, and I put a charge. I put a charge individually. I will put a charge positively charged, and I will put a negative charge here. And both of them will move in the same direction. This will move in this direction, and this will move in this direction with the same velocity. You should be able to tell me, given the fact that there is a magnetic field entering the page, entering the board, in which direction these charges will deflect. Remember, the magnetic forces, they don't make any work because they are perpendicular to the direction of motion, but they change the direction of the velocity. So they accelerate the charges. They don't change the kinetic energy, but they accelerate them because when you make a curve, you feel centripetal acceleration. Remember, the acceleration is not only changing the velocity, the magnitude. No, it's, when you say change of velocity, it could be the change of the direction of the velocity also. So that's what the magnetic force do. The magnetic force changes your direction of motion. If you move, because if these charges don't move, if they are there, they don't feel anything. And I don't know why this thing suddenly jumped. Okay. I believe it was some sabotage, but no, it's not sabotage. Okay. So please, can you tell me, let's do the exercise. Right-hand side rule. Let's apply we will not use the current formula. Let's use this formula, which is the same actually. Charge, velocity, cross product. Magnetic field. This magnetic field is the external magnetic field. It's not the magnetic field generated by the motion of the charge. It's different. It's the external magnetic field. So this charge moves in which direction? Can you tell me? QV cross magnetic field. This charge, positively charged, will move up. And of course, for obvious reasons, if I apply QV cross, technically the right-hand side gives me up, but I have to take into account this sign is negative, so this will move down. This is how you can deflect particles. For example, if you want, I want to separate positive and negative charges, I just throw them all along a magnetic field, and some of them will deflect in one direction, the others will deflect in the opposite direction. Okay, this is how it works. Any questions so far here until now? Okay, this is the review of the magnetic force. Until now, everything clear? Everything clear? I think, of course, I will share with you some examples. I will send to you some examples subsequently, but it's okay. Now, remember the last time I told you that, oh, well, this is important actually. This helicoidal motion, it occurs when there is a magnetic field and you put a charge to move. This is the general motion because there is the charge is deflected by the magnetic field, etc. But what I want to do right now is this part. You have a solenoid. I think we studied this the last time. You remember? North pole, south pole. I approach a magnet to this wire, and the change in the flow of the magnetic field generates what? Generates a current or a voltage. So when I approach the magnet here, let's move the magnet up. Then the magnetic lines start to increase through this solenoid. So the solenoid feeling that, the solenoid feels upset and wants to discount that magnetic field entering. So it generates a current in the direction such that it cancels the magnetic field entering. So let's put it this way. In which direction the current generated here has to point in order to counteract, I mean, to create a counter term action. Exactly, and then it will create a magnetic field in this direction, which will oppose to this. This is if I approach, because there is a change, remember, the voltage generated is the negative of the change in the flow in time of the magnetic field. But phi is the magnetic field times the area. Okay. So this is the flow of magnetic field through this wire. And this is how the transformers operate. Now, I don't know if these guys, they have a transformer here. If no, I will paint. Here you are. This is the principle of the transformer. I think I told you the last time, because when I was teaching, I told you that when the companies, they transmit the electricity to us, what they do? They first, of course, let's put the process here. Let me see the screen here. Let's assume that it's by waterfall. There's a waterfall here. Potential energy of the water, Bernoulli, becomes kinetic energy of the water here. There are some turbines here. They start to move. When they move, of course, that change in magnetic field generates a current in the way how we show it. Because inside this pattern in the center, there is a wire like this, and then there is a magnetic field pointing, and then the fact that this rotates in this direction, it generates a change in the flow of magnetic field. Sometimes the magnetic field points in this direction, but after this turn 90 degrees, so the flow of magnetic field is zero, then after is negative, then after again zero, then again the same, so it rotates, it rotates, it rotates. It changes the magnetic field, the flow of magnetic field drop. So this is what generates electricity in the electric plants, obviously. Nuclear plants the same. The difference is there is no waterfall, it's expansion of a gas. They will not put the toxic products to expand, obviously. They put the toxic products is for generating the heat, which will expand a gas. And that expansion of the gas is what moves the turbine. The same happens with thermoelectrics. Thermoelectrics, they heat some let's say some room, and then that heat expands, generate expansion of some gas, and that gas is the one which moves the turbines. Then, okay, very happy, we generate the electricity, the AC electricity. Wonderful, marvelous. Then, what happened? We had to transmit. It's not only generated, we have to transmit to the houses of people. I want to transmit to you, and I have to charge you money for that because I am doing a job. Then what do? Before transmitted, this electricity generated has high amperage, low voltage. The power of the electricity is, naively speaking, ignoring the phase effects and this kind of thing, is proportional to the current times the voltage. And the losses are proportional to I squared times R. R is the resistance of the cables. And this comes out from replacing V equal IR, remember Kirchhoff and this kind of thing. So for converting the voltage, when I change the voltage, I have to increase it. If I increase the voltage for a given power, I decrease the current, and then I decrease the losses. And if I decrease the losses, maybe I can transmit this to your houses, and you will receive. But before you receive, I have to decrease the voltage again and increase the amperage with the same power. Ideally, of course, the power decreases because there are losses. There are small losses because of this. And you receive that. And in the house is where the energy dissipates completely. Okay? It degrades completely. The entropy increases, which we will see in thermodynamics. So, of course, you use for ironing a sweater, for turning on the TV, turning on the fan, the air conditioner, whatever. Nice. But this conversion is done thanks to these devices called transformers. Okay? They have a primary and a secondary. And between these two guys, there is a material here. There is a material here This material ideally is a material which is able to transmit the magnetic field, facilitates the flow of magnetic field. It could be a ferromagnet. It could be something which facilitates, such that the magnetic field flows and the magnetic field will not want to escape. It will continue here and flow in the opposite. So when you generate changes in the flow of magnetic field here, let's put it this way: you generate this from you generate the electricity in advance. That electricity flow here is alternate current. It flows in one direction and then goes back, and it generates fluctuations in the magnetic flow. So the magnetic flow will go sometimes go up and sometimes will go down. It will be fluctuating. This change of magnetic field is transmitted to the right-hand side. Sometimes go down, sometimes go up. And then here, depending on the number of turnings, because this is a cable, this is a wire, the number of turnings define whether I increase the voltage or I decrease the voltage in this transmission. Because the induced voltage here is proportional. Let's forget the sign. I will put proportional. The magnitude of the voltage created is proportional to the change of the magnetic flow multiplied by the number of turnings, the number of cables or the number of times I can turn this cable. And this change of flow goes to the right-hand side, and again, the same story. So this is the principle. The number of turnings will be different. The number of turnings here is different than the number of turnings here. And this ratio is what defines whether I increase this voltage or I decrease it. The idea is when I go to the street, I increase the voltage for the minimizing the losses. When I rise to your house, we decrease the voltage. Okay. The exact calculation I will send it to you in a moment, but at least you have the naive notion, because I don't think we have enough time. Actually, we almost finished, and I want to cover all other things now. But I think I explained this the last time. The full problem, the full exercise I will send it to you for you to understand what's going on. But you should understand that whenever there is a change in the flow, for example, if I have this magnet and I pull down, the number of magnetic lines is decreasing, and then this guy will create a current which will try to increase that. Actually, it will be the opposite to this current. It will be in this direction, because the idea is to increase it. So I mean, you have to do this exercise. You analyze the problem like this. You see the wire. Let's put this wire here. Simple. I have a magnet here, north and south. The lines, they go like this, from north to south. But some lines can cross the wire. If I approach this magnet here, the number of magnetic lines are increasing. The system will try to decrease them. And for decreasing them, then the current has to move in this direction. You can do the exercise. Right-hand side. The opposite, if I pull down, let's assume now that I pull down, number of lines is decreasing, then this guy will try to increase it. So it will move the current in the opposite direction, which will help to increase. You can do the exercise, because the magnetic field will surround the wire, so we'll enter here, we'll go down, and we'll go up here. So try to do this mental exercise. Every time you have to get used to this. And try to investigate, please, the transformers, how the number of turnings affects whether you increase or decrease the voltage. This is a standard. All the companies apply this, etc., because we don't have superconductors yet for transmitting the electricity ideally. Now let's close this cycle. with the Maxwell equations. I will not cover the part of the displacement current, but I will explain that probably in the next class. The reason why I am searching now these things here is because we have a problem here for finding the. Remember at the beginning, we have some issues with the computer. Well, let's put here Maxwell equations. Here you are. These are the Maxwell equations. That is the, don't get afraid. We will not see what this displacement is. This is, let's ignore here and letter right. Electric field is proportional to rho divided epsilon zero, because this D is just epsilon zero times, or epsilon better. Take into account D is when it's inside a material. For example, the electric field enters in a material. This is the Gauss law. The Gauss law is a Gauss law. In the magnetic field, the divergence is zero. Why? Because there is no charge of magnetic field. The magnetic field doesn't have any charge. So Gauss law again, same. This means that there are no magnetic monopoles. However, remember Dirac demonstrated that in order to quantize the charge, the electric charge, you need to input a magnetic monopole. It's his demonstration. That's the idea. And in principle, if that magnetic monopole exists, it has to be very heavy, because otherwise we have seen it. And the risk, if we have not seen it, maybe in the early stage of the universe, when the universe was more dense and highly energetic, let's say, because of course more density is more energy, probably these particles existed. But nobody has seen a monopole yet. It's hypothetical. When you use Maxwell equations, you put this term to zero because it's in vacuum. Yeah? So the equations become symmetric. Rotational heat, this is the change. It means the change of the flow of magnetic field generates a voltage. This is what we just showed you now. And this last one is a current generates a magnetic field, which we just think. But this term we didn't see it yet. And I intend to explain it in more detail the next class. It's called displacement current. Without this term, Maxwell has not been possible. And this term occurs, for example, when a capacitor gets charged. It's the most difficult to understand. That's why I have not explained yet. But I will explain subsequently. But for the moment, I just want you to understand that from this set of equations, setting this guy equal to zero, we obtain the equations of a wave. Two equations of wave, one for the electric field, one for the magnetic field. And together, these guys are the electromagnetic wave equations, which move at the speed of light. Okay. Let me see. I think here, somewhere, I will show you. Before going into the details, you will see that the magnetic field is moving in one direction at the speed of light. And you will have a magnetic field fluctuating like this, and an electric field perpendicular, moving like this. And the wave equation of this emerges from those set of Maxwell equations I just showed to you. Doing some tricks. Of course, you have to apply the rotational, the divergence in one, blah, blah, blah. Combine. You start to combine these equations in pairs, and you will get two equations of wave. Both waves moving at the speed of light. One describes the fluctuation of this magnetic field, and the other explains the fluctuation of this electric field. And in both cases, the speed of light emerges as a consequence of a quantity which multiplies mu zero and epsilon zero. Actually, mu0, I have not yet done exercises for calculating magnetic field. I think we should do those exercises in the next class, because this class I just focus on magnetic force and calculating the electric field. No, well, I didn't calculate magnetic field yet. Yeah, no, I didn't do those problems. I think those problems we have to do it. I omitted in this class, but we will do it. We will do probably the first 15, 20 minutes of the next class. We will calculate magnetic fields due to the motion of sources. Before going to the Maxwell equation or to the wave equations themselves, look at this. This is the electromagnetic spectrum. And you can see that it has plenty of applications. Look at this. Radio. We use the radio waves? Yeah, we use the radios. Do you know how the radio operates? The radio? Even the TV, no? Yeah, I mean, you have a giant antenna. Sky Tree in Tokyo, for example, is an antenna of radio and TV. You send an electromagnetic wave. Actually, it's a long wavelength, no? Low energy, because for not making damage to humans. That's the idea. We don't use the ultraviolet waves for daily life purposes, because they can degenerate our cells and so on, but they can kill us, generate cancer and so on. So the radio sends the signal with some frequency, some specific frequency. And you have the radio in your house. And you can see that the radio say a set of frequencies in hertz, no? They say da 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 da. If you put your radio in the house at the frequency which coincides with the frequency of the signal, you catch it. But why do you catch it? We will not see that in this course because it's too short, but I will explain naively. Why do you catch it? Thanks to a phenomenon called resonance. Resonance. Do you remember why the bridges? There's a famous video. Do you remember a bridge? When they constructed the bridges before, they didn't calculate so well, and some bridges started to fluctuate like crazy and collapse. Or some buildings were constructed wrong, and eventually they started to shake and boom. Do you remember why was that? Resonance also. Resonance. Every building, everything, every object, and even our device in the house, our radio, has something called natural frequency. Natural frequency, you can calculate. This building has a natural frequency. It's moving, it's oscillating, you cannot see it, you cannot perceive it, but it's moving. If there is an earthquake, in Macau there are no earthquakes, I think, but luckily. But let's say if there is an earthquake, and by chance the wave coming from the earthquake coincides, matches exactly the frequency of the building, the amplitude of each oscillation will become larger and larger and larger, and brah, bada bloom, boom. This is what happened. I will send you the video. There's a video of a bridge that when they constructed, it was quite scary. People were moving and it looked like a blanket when you do the blanket like this. And why was that? Because the bridge has a natural frequency, and the sources of disturbance external, which was the wind, etc., with vibration, has a frequency which matches the natural frequency of the bridge. So every amplitude was larger and larger until the bridge collapsed. One day, brah, fell. Congratulations. And then now we know that the failure was because of a phenomenon called resonance. Every engineering study that. Every engineering student, a study of engineering, they study this aspect. That's the negative part. Well, it's positive because we know how to avoid it. In the radio, resonance is positive because precisely when your circuit, the circuit of the radio, the device you have, matches with the frequency of that, the signal amplifies. And this is a case where the resonance is positive. There are ways to calculate resonance. Actually, the calculation is not difficult. It's quite simple. The differential equations involved are very simple, surprisingly simple, but unfortunately, we don't have a space in this class for going so far, no? Unless we do it in a laboratory or so. Radio. Microwave you use for heating your food. When you bring, I don't know, in Macau, you bring the food from the house and you, okay. Infrared still is not so terrible. Light, this is what we can watch. This is the visible spectrum. Start with red and go to purple. So from all the electromagnetic spectrum, we can only watch this. You're watching me because sunlight impacts me and you see the reflection of the light which I project. But what you see is only this part. You don't see this part. I also project this part, or maybe a little bit the other. Ultraviolet, X-rays is for when you fracture yourself and you go to the doctor to see what happened or which bone you got broken. X-rays. You cannot expose so much to yourself to the X-rays because the energy of these rays is high. Look, you go to larger frequencies. The larger the frequency, the higher the energy. Because the electromagnetic waves are transmitted by photons. Remember, the energy of a photon is equal to h, the constant of Planck, times the frequency. If the frequency increases, or if the wavelength becomes shorter. Why? Because the speed of propagation of the electromagnetic wave is the speed of light. And the speed of light is the wavelength multiplied by the frequency. So if this frequency increases, the wavelength becomes shorter because the speed of light doesn't change in vacuum. Now, somebody say, no, well, the speed of light changes when it enters materials, when it enters the water. Well, this is a misinterpretation, actually, it's wrong. In reality, what happens is that when the light enters the materials, it's absorbed and remitted many times by the atoms. And that creates a delay effect. And that delay effect creates the illusion that the light is moving slower, but it's not moving slower. It's moving at the same speed, only that the atom spends some time absorbing and remitting, absorbing and remitting, absorbing and remitting. Let me connect the laptop because the battery is somehow dying. 1 second. I think we can move this probably without destroying anything. There is a way to connect it. So in this class, we will not be able to cover still the equation of wave, and this class we will be practicing exercises about how the charges, the motion of charges generate magnetic fields, because we need to know also the geometries. There is an analog law called to be similar to the Gauss law, but it's called Ampere, the Ampere law. I think I explained the last time. In here, we have to practice those problems, but let's close up this part. X-rays and gamma. These gammas, they can kill you. These gamma rays, when you are in the space, we are lucky we are in the air, we have the atmosphere which protects us. If we go to the space and we receive directly the radiation, we will receive any kind of radiation, including gamma rays. Directly. Well, this is what I was telling you. X-rays for the bonds. You need to protect for the sun, the visible spectrum. Look at the radius. Look at the wavelength. Typical wavelength of a radio signal, about 10 centimeters. Typical wavelength of microwave, 1 millimeter. Let's go to gamma rays. Picometers, nanometers. So quite short, no? Quite short. Highly energetic. The shorter the wavelength, the more energy they carry. Yeah, higher energy they carry. And it's negative for us, of course. If that energy, that radiation touches our cell, this is what happened in Fukushima. You remember 2011, I was in Osaka actually when it happened. That everybody was escaping from Japan except me. Then what happened? The nuclear plant was exposed, no? Some radiation. That radiation has high energy, short wavelength, or high frequency. And if you are in contact with that radiation directly, it's not that you will die immediately. It will take some time, but your cells will start to decompose, because when the radiation of high energy touches your cells, it creates transformations, undesirable transformation, something which you don't wish to occur, no? Mutations, etc. Look at the speed of light. This is what I was talking about, and this is what creates misunderstanding. In vacuum, 300,000 kilometers per second. In ice, in water, then you say, well, in different medium, the speed of light changes. Relativity is wrong. No, it's not wrong. Because relativity specifies that the speed of light in vacuum is an invariant. And what happens when the light enters these materials is what I told you. They are absorbed by the atoms of the material and remitted. It's a process of absorption and remission, absorption and remission. In that process, there is a delay, and naturally the speed of light. Now, pay attention that the light you see is composed by many frequencies. So sometimes that's why the famous Newton experiment, that they put a light through a white light through a prism, and he could decompose he could divide the light in different colors, because each color has a different frequency, and each frequency moves with different energies, and they deflect different angles. Okay. And this is the definition of a speed of light, of course, what I was telling to you is the wavelength multiplied by the frequency. So this is a way to know what happens. The speed of light doesn't change, lambda, frequency increase, wavelength decrease. The speed of light doesn't change. The speed of light, or let's put it this way, because saying speed of light confuses people. The speed of the electromagnetic wave is better, which is the speed of light, obviously, doesn't change with the energy. When you increase the energy, you change the frequency, you change the wavelength, but you don't change the velocity. The velocity is the same. The velocity of X-rays is the same velocity of the infrared light. The velocity of a radio wave is the same velocity of the ultraviolet spectrum, whatever, even the visible light, right? Now, why we can see the stars? This is important. The electromagnetic waves, they don't need a medium of propagation. I think I said that before. This is the difference between ordinary waves and the waves of electromagnetic waves. No? Do you remember the first class? I think I sent you a video about that. I explained the famous Michelson-Morley experiment that tried to measure the velocity of light relative to the ether, hypothetical ether, which failed, because the speed of light doesn't change in vacuum. No? It doesn't matter how you move relative to the light, it will always move with the same velocity relative to you. What it changes is the space and time. So all the electromagnetic waves behave in this way. It doesn't matter how fast you move. Let's assume there is some electromagnetic wave approaching to me, and I move near to the speed of light. Still, I will perceive that wave is approaching to me at the same speed, which is the speed of light. If I do the opposite, I run away as fast as I can. Oh my God, I don't want to be touched. It's useless. The wave will change you, because still you will perceive that this electromagnetic wave is moving at the same speed, which is the speed of light. The speed of light is just a term. More properly, is the speed of electromagnetic interaction, or because the gravity also propagates the speed of light. So the most appropriate way is to say the speed of propagation of massless particles. It's the most accurate definition. But the speed of light is a term which eradicated the literature, and we cannot remove it. So that's why I have to talk like that. But even gravity propagates the speed of light. And okay. Any questions so far here?
In terms of the practice, are we gonna do it together in classes?
The practice?
Yeah.
Well, for the practice, okay, I will call a few guys to the board next class to see if you can solve. I study these three geometries. I will send the video to you. I study the geometries. That part I will not record. Because anyway, I cannot record everything. No? But before that, I will show how to solve, how to calculate magnetic fields because of the flow of currents or because of the flow of a charge. And before leaving, look at these guys: high energy, lower energy. That's why you have listened that the universe, when it expands, the light moves to the red. Why it moves to the red? Because when it goes away, the wavelength becomes longer, and the tendency of the light is to become red because it arrives with lower energy. The opposite is something approach to you, and this is some kind of Doppler effect in light. It's similar to happen with the sun. No? There is a Doppler effect on sun. When a wave approach to you, the frequency changes, no? because of the velocity. But in this case, the color changes. And what I wanted to say is that thanks God that the electromagnetic waves, they don't need a medium of propagation. Otherwise, the sun will not be able to send us light. The light of the sun will not arrive over our planet because there is no medium of propagation between the stars and our planet. So fortunately, the electromagnetic waves, they don't need medium of propagation. That's why when the astronomers study the galaxies, whatever, the main source of information is the electromagnetic interaction. Now we have gravitational waves. And why is so important the discovery of gravitational waves? Because electromagnetic interaction is so strong. So when it's emitted millions of years away, when it arrives to us, it's not accurate. It receives a lot of scattering interference because it interacts strongly. Electromagnetism has a strong interaction with anything. But gravity is the weakest force. When a gravitational wave is generated from the source, almost becomes, when it arrives to you, is almost the same pure event. Of course, with some change of frequency, something. But I mean, you receive the full information of what happens at that instance of millions of years away, obviously. But that's the importance of gravitational waves. The gravitational waves will allow us, if explored fully, to understand better the universe. It's like you see these guys who go to the archaeologists, no? Archaeologia. They go to study the past when they excavate. Well, it's some kind of archaeology, but for the universe. So that's the importance. So the level of the interactions matters at the moment of studying the history of the universe. So now I will close the class with this. Next class, I will show you the wave equations derived by Maxwell. I will show you the derivation, and we will practice a little bit what is means, no? The magnetic fields, how calculate. And we will jump immediately to thermodynamics. Thermodynamics is the next subject to understand. So any questions so far before leaving? Different to the question you asked?
They have to practice questions in advance because to be honest, I feel like these two sessions, a lot of things is quite a strap to me because this is the first time I heard of it. I'm still.
Sure. You will have some problems. I will send some sample problems to you. I think I can send you this week some sample problems for you to practice. Also, check it out the video of this because you can see the steps, no, for developing some problems. That's it. But yeah, you will have many samples. Anything and any question you have, you can come to me anytime. And so then I close this session. I will finish this